Alright, in this video we're going to be finishing up the special Maclaurin series. This is where we left off from our last class on Thursday. Last class we derived the Taylor series for e to the x, as well as our Taylor series for cosine of x and sine of x. We begin talking about the manipulation technique, so I'm just going to pick up our notes from here. There's some notes to include here at the top that kind of walk you through some scenarios. So substituting, multiplying or dividing, adding or subtracting, and then taking a derivative or an integral. These are the techniques we want to be using today on these series that we have. What this part says is that the radius of the convergence is the same for the original and modified series, except at the endpoints. So the radius is technically the same, and the interval of convergence is very similar. The only thing you'd have to do is recheck the endpoints if you wanted to show what it does at those values. So for part A, it says find a Maclaurin series for f of x is sine of x squared, and give the first four non-zero and the general term. Now, the sine of x is given by all of the odd values, so that's going to be x minus x cubed over 3 factorial, plus x to the 5 over 5 factorial, minus x to the 7 over 7 factorial. The general term will come in handy when trying to construct the new general term. To generate the odd values, we generally use 2n plus 1. This assumes that n starts at 0, so n starts at 0. In order to verify that n starts at 0, or if you ever forget, remember you can just plug in. If you plugged in 0, you'd get x to the 0 plus 1 over 0 plus 1 factorial, which just simplifies to x, which is correct. Now we're trying to find the sine of x squared instead, and to do this is quite simple. We're just going to replace all of these x's here with x squareds. Remember to use parentheses, otherwise you may get the wrong answer. So really we're saying x squared, quantity cubed, and so forth. X squared, quantity to the 5, and x squared to the 7th over 7 factorial, and then plus dot dot dot, plus x to the 2n to the 2n plus 1, all over 2n plus 1 factorial. Now, I think it's clear that the n also starts at 0 because the term that used to live in spot 0 is now occupied by x squared, which is also related to spot 0. So I think we're doing just fine with the starting value of n being the same. The one thing that I will say is that you may not see this format on a multiple choice, so let's go ahead and make this multiple choice friendly. So this is FRQ smiley face, meaning there is no need to simplify these any further. Instead, let's go ahead and consider what MCQ smiley face would look like. The MCQ smiley face would be perhaps to distribute the 2 to this as well. So we have, I accidentally put an n here. So that should just be x squared to the 2n plus 1, which makes sense because we were plugging in x squared the whole time. Now distributing that 2 out, we would then get x to the 4n plus 2 over 2n plus 1 factorial. And that would be your MCQ smiley face. So we've given the first four non-zero terms, the general term, and we are good to go. It says use your answer to A to find the Maclaurin series for f prime of x. Now f prime of x we could find if we wanted to. In fact, we might do that just for fun to see the answer and how it compares. However, let's just do it the simpler way, which is we just need to take the derivative of all of these terms and this formula here, and to get our answer. The derivative over a bunch of terms is very nice and simple because the minus sign allows us to split them up. So that every time you see a plus or minus, every time you're in different terms, we just do the derivative of each individual part. The derivative of x squared is 2x. The derivative of this thing here, well, it might be easier to simplify it. So let's go ahead and write some more MCQ-friendly versions of all of this above. This will allow us to take the derivative a little bit easier as well. So now I do see value in simplifying, so I'm going to go back and simplify. So once again, in blue we have our MCQ smiley face, and that's what we can use to answer our question here, just because it's a little easier. So we get 2x minus 6x to the 5 over 3 factorial plus 10x to the 9 over 5 factorial minus 14x cubed, or sorry, to the 13th over 7 factorial plus dot dot dot. And then now we want to take a derivative of these terms here. I'm going to do something a little weird, which is, oh here, I'll just do it the normal way. The derivative of this would be 4n plus 2. We bring the number down. It would be x to that number minus 1, so 4n plus 1, all over 2n plus 1 factorial. Although these look like they can't simplify, if you factor a 2 out of this value, you definitely could simplify. It'd be 2n plus 1, x to the 4n plus 1, all over 2n plus 1 factorial. The 2n plus 1 factorial and 2n plus 1 are going to cancel out partially. Specifically, the 2n plus 1 part would go away, leaving us with 2x to the 4n plus 1 over 2n quantity factorial. That would be our final answer for like MCQ type smiley face again, meaning like you've simplified everything. What I think is kind of interesting is that this also means that this has to be f prime of x. Now recall that f of x was defined as sine of x squared. Since f of x is defined as the sine of x squared, the derivative of the sine of x squared would be given by the function 2x cosine of x squared. Now what that means is that if you wrote out the expansion to cosine of x squared, just kind of like we did in a, but change it to cosine, then you multiplied by the value to x, you should get this formula down here. Now, that looks kind of crazy to think about, but I think I kind of see it already happening. The cosine of x squared would be the exact same formula as this one right here, except it would be the even values. The even values would be x squared to the 2n over 2n factorial. And then if you multiply that by 2x, think about how this could all work out. These are really equivalent because you get 2x, x to the 4n over 2n factorial, which is the same as 2x to the 4n plus 1 over 2n factorial. Now I think this is kind of a cool connection because it really does show you that the manipulation techniques are valid, at least one example of the manipulation techniques being valid. In case I just lost you with that last thought, what I was just trying to say is as follows. We did the expansion of sine of x squared, and then instead of taking the derivative of sine of x squared, we took the derivative of that expansion, the expansion being all the polynomials, and we got this answer at the end here in green. Instead, we could have done the calculus up front and taken the derivative of the function, and then done the expansion second, and guess what? It results in the exact same thing. Just kind of a neat idea, and kind of shows you the purpose, or one of the things that this unit allows you to do. Okay, for our next one, find a Maclaurin series for f of x is e to the x plus 2. Give the first four non-zero in the general. Now, it might seem nice and easy that, oh, we just need to plug in what e to the x is and put in x plus 2. Unfortunately, that would not give us the correct answer because then we would be generating a series that is not centered at 0, but instead centered at 2. Meaning, if you thought, oh, life is simple, you just plug in x plus 2 everywhere, this is not a Maclaurin series. This is not a Maclaurin series because its center is -2. So instead, we have to think of a different way. And the different way is just a really simple manipulation. This is really just e to the x times e squared, meaning we can expand e to the x as 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, plus dot dot dot, plus x to the n over n factorial, plus dot dot dot. All of this is going to be multiplied by this quantity e squared. This quantity e squared is going to go at the end. And then we could just write down our final answer. It would be e squared plus e squared x plus e squared x squared over 2 factorial plus e squared x cubed over 3 factorial plus e squared x to the n over n factorial. There's some dots in here and some dots in here, and all is good. Once again, we start with some n equal to 0. Since that term didn't get deleted, it stays n equal to 0. If you wanted to check, just plug in 0 over here, and notice that we get e squared x to the 0 over 0 factorial, which is just equal to e squared. For part B, we're taking our answer from A and instead subtracting off e squared. Now the e squared there is not just a random choice. The e squared down there is to say that that's weird. The lasso tool isn't working. I was just trying to copy paste. Give me a second. Okay, we'll just have to rewrite it. Um, the value we got above in blue, I'll just copy down real quick, and I think you can probably see what's going to happen. What's going to happen is just one of the terms is going to cancel, specifically the first one, the e squared term, because you're subtracting off e squared. And that lasso tool would have been really nice, because I wouldn't have to write this again. But I guess that's okay. You don't get the lasso tool unless you're on a nice piece of technology as well, so all is fair, I suppose. The e squared here and the e squared here are going to cancel. Notice that since we're just subtracting off a term, we're not really affecting any of the other ones except that first one that was in common with it. As a result of that, we really don't get a difference to our general term. We don't get a difference to our general term, so what really difference did this make? And the answer goes back to this. These guys started off n as 0. We just eliminated the n as 0 term. So this formula is correct as long as we state that n starts at 1. Starts at n is 1. The reason why we have to state that, if we plug in 1, we now get the bottom value of e squared x, because e squared x to the first over 1 factorial. And really, we do want to show that it did something. And the something it did is eliminate the 0th term. All right, for our next one. Oh, I don't know why there's this sign of x hanging out down there. Must have not got erased. So we'll just pretend that doesn't exist. Okay, good. The sign of x plus e to the x, our job is to write the first 4 non-zero terms of the Taylor series about 0. Remember that the Taylor series about 0 is just another way of saying the Maclaurin. And remember that if it doesn't ask us for the general term, we don't have to write the general term. Instead, we just do something quite simple. The sign of x is going to be equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. We could write the general term here, but once again, we don't need to because it doesn't ask for it. E to the x we've written above. If I had my lasso tool, it'd be worth scrolling. Unfortunately, I don't. Luckily, it's a simple one to write. Now, if we're going to add these together, let's go ahead and do that. Let's add them together in red. The sign of x plus e to the x. So the sign of x plus e to the x. And I'll color code the right side so you can see where we're pulling the terms from. We're going to try to stick to the order of degrees. So noticing that the 1 is the first one and there's no constant term in there, we're going to get a blue 1. Then we can do our linear terms. We're going to get a blue x and a green x, the blue x coming from e to the x, and the green x coming from the sign of x. For x squared, we're only getting the blue one, so that would be plus x squared over 2 factorial. For the x cubes, we're going to get both of them. However, we're going to notice something interesting may happen. The interesting thing is that they are going to cancel. Because they cancel, that technically doesn't quite count as a non-zero term, so we have to go to one more. Notice that I'm not counting these as two different terms because they should really be combined as like terms. So we're going to have to expand one more, so I'm going to go here and do x to the 4. Now, I could expand this one more as well, but it's already at degree 7, so chances are we don't need to. We know that our next term is just x to the 4 over 4 factorial, because there is no sign for any even exponent value. Our final answer is what's shown. Most likely it'd be simplified, like on an MC, so we get the following idea. All right. So just remember when you're adding series up, you kind of expand them both and then add them second. When you're multiplying series, you can do the same thing, like how we did here. We're expanding e to the x. We don't need to expand constants like e squared because they're just going to be e squared. The derivative of all of it would be 0. It would just be the constant term in a Taylor polynomial. All right, for our last part, we're trying to do x cosine of x. X is nice and boring. It's itself. Cosine of x can be expanded. The cosine of x is all of the even terms. The even terms are going to be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 2n all over 2n factorial. Now, once we have that, we just need to multiply all of that by x. I missed my lasso tool. Can I click these? No? Okay, that's fine. X times the cosine of x would just be x times all of these things we wrote here. So that's 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus dot 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 plus x to the 2n over 2n factorial. Let's go ahead and distribute that x to everybody, and I think life will work out just fine. It makes for quite an easy simplification. We just get x minus x cubed over 2 factorial plus x to the 5 over 4 factorial minus x to the 7 over 6 factorial plus dot dot dot. When you multiply x by x to the 2n, that's multiplying two things with the same base. When you multiply things with the same base, you add their exponents. There's a hidden 1 here. So as a result, we're going to get x to the 2n plus 1. The 2n in the bottom is still the same. And we are good to go. And similar to before, since this one started at n is 0, and all we did is transform it without canceling, this guy also starts off at n is 0. If you don't believe me or just like to verify, you can just plug in n is 0. You'll get the following expression, which is just equal to x. Remembering that 0 factorial is not a trap, it is not meant to throw you off, it is defined as 1 for no deep reason other than by definition. In our last one, our job is to integrate and find the Maclaurin series for the integral from 0 to x of this series, this like collection of terms. Now when we're integrating, we can go term by term, which is very nice. I know it says from 0 to x, but notice that if you plug 0 into any of these, you're going to get 0, and that when you integrate, you just add an exponent anyway. You're adding 1 to all of these as a power rule. So realistically, there's not too much point in focusing on the 0 down here. As a result, we're just going to take the first 4 integrals of these specific terms, and then take the integral of this general term. The integral of the first 4 specific terms is going to be x squared over 2 minus x to the 4 over 4 times 2 factorial plus x to the 6 over 6 times 4 factorial minus x to the 8 over 8 times 6 factorial plus dot dot dot. Now when you go to integrate this function, you want to add 1 to the exponent and divide by the new value. If you add 1 to 2n plus 1, you get 2n plus 2. You want to divide by 2n plus 2 because that's the rule of integration. And you want to carry over the 2n factorial because that's what's there to begin with. You can verify this is correct and check that our starting value is 0. When we plug in 0, when we plug in n as 0, we get x squared over 2 times 0 factorial, which is x squared over 2, which is also correct. Because if you look over here, that's exactly what we have. All right, that was finishing the notes from last time about manipulating and special Maclaurin series. Hopefully this helps, and we have one more video to go over the new material, which is geometric power series.